Okay, so here's our second calorimetry example. We've got a neutralization reaction going on here. Ammonia and hydrochloric acid, that's our base and our acid, and we've got a certain amount of energy associated with this reaction. So remember from our discussions earlier that this amount of kilojoules is associated with 1 mole of ammonia and 1 mole of hydrochloric acid, and that this is an exothermic change because we see the energy appearing on the product side. Okay, so much like our previous example, we've got our system and our surroundings. That's lovely. So our system is our reaction, our neutralization reaction. So I'm not going to write the whole reaction out because it's right here. So our neutralization is our system. And again, our surroundings are water. And it might not seem like we've got water because we're mixing ammonia solution and hydrochloric acid solution. But we are making the assumption, as I said in the original lesson, that for a dilute solution, we're going to treat those as if they were water. So even though we're only putting two things in the calorimeter and they're both solutions, one our acid solution and one our base solution, most of the molecules you're putting in the calorimeter are water. So water is our surrounding. This is different from our previous example because it's asking us what temperature change is expected. So we actually want to know what is delta T. That's the value that we're after. So we know from our equation Q equals M, sort of an M, MC delta T, that delta T is going to be equal to Q divided by MC. We do know the mass of the water. We're going to say, what have we got here? We've got 145 milliliters of ammonia solution and 255 milliliters of hydrochloric acid solution. We're going to make the assumption that the density and the C value and everything is the same as if it were pure water. So we have 400 grams because there are 400 milliliters in total. And we know what C is because we're going to assume we've got pure water. Oops, joules per gram degrees Celsius. Q is the missing link here. We do not have Q, so we cannot calculate a temperature change without Q. Much like the previous example, we were going to relate Q to delta H for this reaction. If we take a look at this one, this is an exothermic reaction. The neutralization is exothermic, so we do expect energy is going to be transferred in this direction. Energy is being evolved by our system during the reaction, and it's going to be absorbed by the water. So we expect that the temperature is going to go up of the water, so that's a good thing to think about. What we know about the neutralization is how much stuff we're mixing together, and we also know this value here. So we know that delta H for neutralization of 1 mole of ammonia or 1 mole of HCl, it would work for either one because it happens to be a 1-to-1 mole ratio, is minus 53.6 kilojoules per mole. So we've got that value. What we really are after is delta HR. I think I'm going to put the sign on here, so they're going to have opposite signs. We don't want to forget that. So let's see, if we want to know this value, and we do have this value, if we know how many moles are reacting, we can get to our answer, because delta H for this reaction is going to be the number of moles times heat of neutralization, or the energy change associated with 1 mole. Interestingly, we got to think a little bit about stoichiometry, and just to make a long story short, we need to find out how many moles of ammonia we've got, how many moles of HCl we've got, because we sort of need to know what's the limiting reactant. The number of moles will be concentration times volume for you formula people out there, and we are given a concentration and a volume for each of them. So if we take a look at ammonia, the concentration 0.2 moles per liter times the volume, which is .145 liters. So let me write this out. 0.200 moles per liter times 0.145 liters, and this gives us 0.0290 moles. If you do the same process for HCl, the number of moles for HCl is 0.063 something something. Can't really read my own writing. So we have about 0.029 moles of NH3 and 0.063 moles of HCl. Because we have a 1-to-1 ratio in our balance equation, we can say definitely that NH3, the ammonia, is limiting because there are fewer moles present of NH3. Once these 0.029 moles of NH3 get used up, whatever HCl is left over isn't going to be doing any kind of reacting. So this is how many moles we've got to worry about for our reaction. 0.0290. So what we can do is we can take that number and sub it back in up here. 0.0290 moles times this value up here, minus 53.6 kilojoules per 1 mole, and that gives us a value of minus 1.55 kilojoules. Minus 1.55 kilojoules. That's the amount of energy that we expect will be associated with this change, with the values that we have. Okay, so we've got our HR, which means we've got our Q. That's how we relate our system to our surroundings. Our neutralization is going to release 1.55 kilojoules of energy, and that's going to be absorbed by the water. So we can take that back over here and we can say that Q will be equal to 1.55 kilojoules. I've changed that to a positive value because the heat's being absorbed over here. It's endothermic, what's going on with the water. And so now we can solve for delta T. We have 1.55 kilojoules divided by the mass, 400 grams, and the C value, 4.19 joules per gram degrees Celsius. I see one problem with that, and that is our units. So because we have units of joules down here, isn't it a good idea to write down units? I think it's a good idea to write down units. So you can catch mistakes like that. 1,550 joules divided by 400 grams divided by 4.19 joules per gram degrees Celsius. And what I get from my temperature change is 0.925 degrees Celsius. Pretty small temperature change. Not a lot of energy evolved from that neutralization reaction. So that's another nice example of what you can do with calorimetry. Again, separating the system from the surroundings, what's going on with the water, keeping it separate from the other, and then just keeping straight what's happening. Making sure we can tell the difference between our molar enthalpy for our reaction that we get from, in this case, from our equation, and this one here, which has to do with the specific amount on this, specific day, a certain amount of energy for a certain experiment. All right, I hope you enjoyed, and good luck working on your questions.